Hello again, and welcome back to MaxIm DL training. I've got MaxIm DL version 5 already up and running, and today's topic will include a discussion about the FITS header. That's the Flexible Image Transport System FITS header, which is a piece of information that everybody should know about when doing astronomy. And also the information window, which is something that MaxIm DL provides in order to eke out a little more than what meets the eye. And I think both of these windows and both of these sets of information are very similar, so I'm going to combine them into this one talk for you today. But first we need to open an image. I've got a nice convenient image here of Messier object number 67, which you might know is an open cluster. So I'm going to open this image in MaxIm DL. I have it here in my Windows Explorer. I can just drag that onto MaxIm DL and let go, and it will open in MaxIm DL. And remembering that we can zoom out using our scroll wheel on our mouse, I scroll out and I can see the actual open cluster pretty nicely there. If you don't like the way it looks, you'd like to see maybe some more stars, you can change it using the screen stretch window as discussed earlier, and so you can start seeing some of the detail here. I'm going to put this on high mode, the preset value in the screen stretch menu for high. And then I'm going to zoom in just a bit more into the center of the cluster so that I've got that visible for us all to look at. Now, the FITS header window. If you go to the View menu, there's a selection for FITS header window, or you can use keyboard shortcuts and hit Control plus the F key, and it will open this window for you with a couple of tabs, the View and the Edit tab. Let's leave it on the View tab for now and take a look at what this has to offer. The Flexible Image Transport System was developed a long time ago by physicists and scientists to transport data files, and they were not always image files. In this case, all of them are these days, but they weren't always image files, and as such they could communicate all sorts of information. There are a bunch of standard headers or tags that are used in the FITS file, so let's go through the most common ones and leave the more esoteric ones for later in our training. Probably the most important one right off the bat is the name of the object. The target object name is equal to M67, and then after that there's a /, and it says target object name. Everything following a / is a comment. Just like in programming languages, the / in this case means the start of a comment. The telescope used is the next line. It says telescope RCOS 10 RCA. It's a rich accretion made by the RCOS Optical Systems Corporation. The instrument that took the image is an SBIG STL 6003 version camera, CCD camera, and the observer was an automatic observatory, in this case my Granger Robotic Observatory. There are no notes appended to this image, it's just an empty field. Also important, the date of the observation. Here it's 2011 March 28th at 0009 minutes and 26 seconds. And notice that this is an ISO 8601 standard formatted field for date, and it gives it to you in coordinated universal time. And it's of the start of the exposure, not the end. It's the start of the exposure. Some software will report the beginning of the software exposure, some will list the middle, and some will list the end. It's important to know which when we start doing precise measurements of times of events, like variable star brightness changes and things like that. We try to average it out and go for the middle, but this software will handle that for you automatically, as we'll see later. The length of the exposure in seconds is 6 times 10 to the first. I know it's a little bit odd. We use this notation where the capital E means to the first times 10 to the first power duration in seconds. The actual duration of the exposure is also 6, and that's good. That means that the exposure wasn't terminated early. The exposure time could have been set for 10 minutes, but the actual exposure could have been only 6 seconds or something like that, because clouds rolled in and the astronomer decided to cut the exposure short. The true exposure time is exposure, right here. This one right here. CCDs are kept cold to reduce noise from their temperature, from their heat. It turns out that all objects, like books and tables and chairs and cameras and people and cats, all have a temperature associated with them, and because they have a temperature, they tend to radiate light. Most of the light being radiated is infrared, so we cool this chip down considerably. The set temperature here was negative 30 degrees centigrade. And so, of course, there's the next entry. The actual CCD temperature as measured on the chip is this very long and precise number, negative 29.72, etc., degrees centigrade is the actual temperature. It's good to take a look at that. If it's close, if it's like 29.7 and 30, those are close values, then everything is running normally. But suppose you set the temperature to negative 100 and it was maybe a 100-degree day out there, a nice hot summer evening. You may not be able to get the CCD temperature all the way down to your set point. Therefore, you may see negative 5 degrees centigrade when your set temperature was negative 100. You never actually achieved the true temperature that you were expecting. The X pixel size and Y pixel size values tell the astronomer the actual dimension of the width and height of the pixels on the CCD camera. On this camera, they are both 9 microns. That is, the pixels used in this particular camera were square. They were 9 pixels wide and 9 pixels tall. That becomes interesting and useful when you start measuring the distances from one object to another using the distance rule. You have to know whether those pixels are truly square or not. We can then scroll down just a little bit here. I'm using my mouse scroll wheel. And the next most important object here is filter. It's a V filter. There are different types of filters that your observatory will provide to you. In this case, V stands for visual. It's a type of green filter used in photometric astrometric reduction. There are also reds, greens, blues, hydrogen alpha filters, oxygen 3 filters. You name it, there are filters for it. There are even ultraviolet and infrared filters. The image type is a light frame. We haven't discussed the difference between light frames, dark frames, and flat fields or bias frames yet, but a light frame is your most important frame. The light frame is the picture of the object you're interested in. Your object RA and object declination are the measurements of the location in the sky that the picture was aimed at. So when the photograph or the image was taken by the telescope was pointed at right ascension of 8 hours, 50 minutes, 48.12 seconds. And it was also hopefully pointed at positive 11:49:01.2 declination. Now, that is always hopeful, but when you start getting to the nominal altitude and azimuth, this changes frequently. This is the actual altitude of the image above the horizon, and the azimuth relative to true north being 0 and south being 180 degrees. So this object was 55 degrees above the horizon, and we were aiming to the southeast at 151 degrees. As we start going further down here, another interesting entry is air mass. This is 1.2 times 10 to the 0, which means that we're looking through 1.2 times the thickness of the Earth's atmosphere in order to see the object. Air mass becomes important because the more air you're looking through, the redder objects look. It's very slight, but in astronomy we can measure that. You can scroll down a little bit more. You get into the date and time of the observation, the UT time and date of the observation. We also get to the latitude and longitude of a variety of things. All the rest of this that comes down here, all the rest of this information is what we call geodetic information using the world coordinate system. You may see WCS here. You might also see the word pinpoint, which is a piece of software that solves the plate for astrometric reduction. That is, it knows exactly where this picture was taken. So that's the View tab. In the FITS header Edit tab, you can actually make changes to some of the things in here. And I suggest that people do not make changes in here unless you know what you're doing. You may want to add notes. You can scroll down and find the notes section and enter some text. And you'd be all set, and you can just hit set, and it makes the change for you. And then you can close it, and it will always be there. Maybe you want to put the name of the observers that took the image, or the school that was associated with the image. The next window I'd like to show you today is the information screen, or the information window. Once again, from the View menu, choose Information Window, and this rather interesting window pops up. Also, your mouse cursor has changed. Instead of being just a little cursor with an arrow, it's now a series of circles, which is interesting in and of itself. I'm going to zoom in so you can see the circles a little bit better. And you'll see also that in the information window over here, that values are constantly changing as I move my mouse over different objects in the screen. Let's put the mouse over that one star and then go look at the information window. It gives you the cursor value, x equals 1038 and y equals 910. It shows you where the cursor is pointed. It also says the pixel value. That is, what is the brightness level of the pixel that the cursor is on. It's 2146.0, which means it's closer to black 0 than it is closer to pure white, which is 65536. The maximum and minimum values are the maximum and minimum pixel values of the pixels inside the innermost circle of my cursor field, those little annuli that we have there, those little circles that we have. The median and average presents the median and average pixel values of all the pixels located in the innermost circle where my cursor is located. The standard deviation presents you a standard deviation of those values of median and average. The centroid is an interesting one. The centroid gives you an x and y position on your image of the object over which you're hovering. What it does is it takes a weighted average of the pixel values, the brightness of the pixels, and determines exactly where the center of that object is located. So I can hover my mouse around a little bit and the centroid doesn't change a whole lot because it's still measuring the brightness of the star that is inside the innermost circle. In this case, the centroid is 1036.635. Yes, it's actually measuring decimal places of pixel widths. That's how good the software is. It's pretty amazing. So if you're looking to get a very precise location on a plate or an image of a star, look for the centroid value. We'll talk about the full width half maximum value later. Here it's 2.472. It's a measure of the brightness of an object in terms of how sharply focused you're looking at here. We'll worry about that later. The magnitude, intensity, signal to noise ratio, background average and background deviation, and flatness are all relative values. It's trying to present a value of the magnitude or the brightness of the star in the field, but this image has not been calibrated yet, so it's just a random number at this point. And we'll talk about how to measure magnitudes later. Let's change the mode here to look at the region. Region actually presents us with some more just general values. This is a choice used more with color images, because if it was a color image it would show you the actual pixel intensities of reds, greens, and blues in the individual image. If we choose area, you're then presented with the option of clicking and dragging open a box. and it will give you the maximum, minimum, average, standard deviation, and total value of the monochromatic pixels here in this region. And it also gives you the height, diagonal size, number of pixels, etc. within the region. If you don't select anything at all, it gives you the complete area of the actual total image from 00 to 3071 by 2047. And in this case, that's pretty cool. It actually says that there's one pixel which has reached maximum brightness of 65535.0. I don't know where that pixel is, but it's somewhere on this image. Lastly is the astrometric mode for the information window. And this is pretty handy if you're measuring the positions of asteroids or planets like Pluto. You can actually put your mouse cursor over a star, and it will not only give you the X and Y coordinates, here 1036 by 949 for the cursor, 1034 by 947.684 for the centroid, but it will also give you the right ascension and declination of those values from the pixel to actual right ascension and declination in the sky. So the centroid value for the star, the right ascension is 8 hours, 51 minutes, and 20.14 seconds, and its declination is positive 11 degrees, 50 minutes, and 23.2 seconds of arc. Very handy indeed. So those are two very functional and very useful windows. I hope that you remember that, because we're going to be using those an awful lot in the very near future. And with that, I bid you farewell and stay tuned for the next training video.